Howdy. The point of this video is to talk about diffusion, and specifically we're going to talk about Fick's first law and where does it come from. So diffusion talks about the ability for atoms or molecules to move around within a volume. This is going to happen if molecules or atoms are soluble within some other phase. That is, can we readily dissolve those atoms or molecules within the solvent or the surrounding phase? Now, you know from experience that if that's the case, and if we start off with a region of high concentration, then these atoms are going to tend to move. And they're going to tend to move towards regions of lower concentration, so that over time, I get a chemically homogeneous mixture. And this is exactly what Fick's first law is telling us. It talks about the rate of diffusion flux, so we call that J, as a function of the compositional gradient. So we would call that dc dx, the change in composition with some geometric direction. But where does this come from, right? Because diffusion on an atomic scale is a random, disordered process. So there's nothing that's telling, hey, you atoms, you have to move over here. So what is the origin of this macroscopic law? And that's what we're going to talk about. So let's think about a solid. And let's say I have a plate of some sort of thickness. So x is going to be my thickness. That's my geometric dimension in this case. And let's say I start off with one half of the plate having a high concentration of some solute phase. This could be hydrogen or it could be carbon, or it could be a number of other things. And let's say the other half has a lower concentration. Now you know from your experience that if I let this system equilibrate, we're going to have flux from this side to that side. But how does that happen? Because on an atomic scale, atoms are moving around randomly. So let's go through a thought experiment. Let's break this whole plate up into individual bins that each have some small thickness. We can call that delta S. And so we have a whole bunch of thin plates over here that have a high concentration, and then a bunch of thin plates over here that have a lower concentration. So what happens within a given time step? All of the solute molecules within this thin volume are going to randomly move around. And there's some probability that some of those molecules will cross the boundary into the neighboring bin. But there's also a probability that some will cross the other boundary, right? And this is going to be independent of the concentrations on either side, because on an atomic scale, these atoms are just moving around randomly. So the same thing would happen in the lower concentration bin, right? But there's still some probability chance that an atom will move over here, or some probability chance that an atom will move over here. But this flux, this transport of solute atoms from this bin to the left or this bin to the right is going to be smaller than it is over in this case. And that's simply because we have less atoms to begin with, right? The overall concentration of solute is much less. And so if I give each individual atom some constant probability of staying in the bin, bouncing out to the right or bouncing out to the left, then that's going to result in smaller fluxes in this case and larger fluxes in that case. So what happens as we get to the interface? Well, I can do this same approach for this bin here, and I'm going to have a small concentration flux moving to the left. But from the left to the right, I'm going to have a larger concentration flux. So in the constant compositional gradient regions, these probabilities will cancel each other out. The probability that an atom moves from here into this bin is going to be the same as an atom moving from this bin to the left. Same thing over here. But at this boundary, I have a much smaller average flux from, let's say, bin 2 to bin 1 than I do from bin 1 to bin 2. And I can represent that by arrows showing the proportional to the flux. And so what this means is that within a given time step, I'm going to decrease the concentration here and increase the concentration here. right? So it's going to look something like this. Now remember, on an atomic scale, all those atoms are moving around randomly. They're equally likely to move to the right or to the left. But what is changing our compositional gradient here is the fact that if I do have a gradient, I'm more likely to move downhill than I am to move uphill. And so we could do that, this experiment again. And again, we have a large flux from bin 1 to bin 2. We have a moderate flux from 2 to 3, maybe a moderate smaller from 3 to 4. But in each case, the flux in one direction, from left to right, is larger than the flux from the right to the left. And so what we end up getting is a case where we can measure, what is the flux over some finite thickness. And for the exact reasons that we just described, this flux, which I described by the letter J, and that's going to equal the mass per unit area per unit time. So this would be a mass flux, is going to be proportional to the concentration gradient, dc dx. So if I have a large discontinuity in the solute concentration, I'm going to have a large flux across that small thickness. If I have a concentration gradient that is more spread out, dc dx is going to be smaller. So that would just be the derivative, the slope of this line. It's going to be smaller, and my overall flux is also going to be smaller. Now there's one thing that we haven't talked about yet, and that's this constant. So I keep saying that the flux is proportional to this compositional gradient. And what is controlling that proportionality? Well, that's a function of a number of things. It's a function of how easily does this solute species move around? Is it a small atom that can move fast? Is it a larger atom? What is the diffusion mechanism? Is it interstitial or is it substitutional? What is the crystal structure that we're diffusing through? So a lot of things come into play that affect this diffusion constant, and that's what we call T. Okay, so in summary, remember that Fick's first law of diffusion, it's controlling the flux, and it says the flux is inversely proportional to that concentration gradient, so atoms are moving downhill. And we get there by thinking about random atomic motion at each individual very thin layer. So atoms are always moving, and they're equally likely to move in any particular direction. But if we take an average of all of that motion, we're going to find that it's going to move downhill, and it's going to be proportional to that compositional gradient.